section 2.4.2, the energy of a point charge distribution. In the last video, we talked about the work that we needed to do to bring in a charge and place it within a set of other charges. Okay. That work was related to the charge that we're moving and the potential of that charge, or the potential where that charge lives in its final resting place. But we have to build charge distributions. The natural question would be, well, how much work does it take, or what's the energy required to build a distribution in the first place? And then we can bring in more. Okay, so for an entire collection of point charges, how much work does it take to assemble? All right, let's build it one by one. I'm going to bring my first point charge in from infinity. Right, that was the assumption of this expression right here, that we started everything at infinity and the potential at infinity was 0. And I'm going to bring it in, and I'm going to place it at some point, call that the position of charge 1. And well, the potential at charge at R1 before the existence of any charges is 0, so it would take 0 work to bring in that charge from infinity. Okay, so the work done to bring the first charge is 0. That one's for free. Okay, so now we have a charge at R1 with magnitude Q1, and we want to bring a second charge in, Q2, and we want to bring it to some spot, R2. Right, well, now it's going to feel the potential from charge Q1. All right, this distance here is, I'll call it R12, because it's the distance between 1 and 2. So the work required, or the minimum work required here, is just the potential from charge 1 times the charged Q2 that I brought over. All right, potential times charge, potential times charge. Okay, now I want to bring a third charge. I'll bring it, put it over, running out of space. I have R1, Q1, I have R2, Q2, and I want to bring a charge Q3, put it right there. We'll call that R3, Q3. All right, and now it feels the potential from both of these point charges. So that's 1 over 4 pi epsilon naught Q1 script R13 plus 1 over 4 pi epsilon naught Q1 script R23 all times Q3. All right, and you can see if we do this a lot of times, it's going to be kind of a pain in the butt. But we can write a generic expression, which is that the work required to bring in some number n point charges is going to be the sum of all of my charges times the charges that already existed when they were there, Rij. All right, so I can do that sum, although that's not very nice looking. What we can do instead is go ahead and say, all right, well, what I'm doing here is I'm purposefully avoiding double counting because I don't want to double the energy on accident. But I'm going to be okay with double counting, and then I'm going to cut the value in half in the end. So I'm going to go ahead and introduce a factor of 1/2, 1 over 4 pi epsilon naught, I equals 1 to n, j equals 1 to n, making sure to avoid counting yourself, qi, qj, rij. Okay, so now this sum is going to include twice as many terms as the previous one, but we're accounting for that by dividing by 2. All right. This qi doesn't depend on the second sum, so I can bring it out. 1/2, 1 over 4 pi epsilon naught, I equals 1 to n of qi, j equals 1, j not equal I, qj over rij. Well, this bit combined with this bit is the potential at Ri. 1/2 I qi v of Ri. Right? So by starting with the 0 charges, we brought them in one at a time, calculated the work that are required to bring in each charge. We created a nice closed form of that, which turns out it's just related to all of the charges, bringing them in, and the potential at those points. It looks very similar to this expression here. It's not quite the same, but it looks pretty close.